in this example, we're going to graph the piecewise-defined function h. We can see that we have h of x here, and h of x is equal to, and then on this right-hand side, we're going to see that there are three different pieces by which h is defined, and it's defined by three different pieces on three different parts of its domain. So we see h of x is equal to, and then that first piece is defined by negative x squared plus 4 if negative 3 is less than x, which is less than 3. And the second piece is 2x minus 5 if 3 is less than or equal to x, which is less than 4. And the third piece by which it's defined is just negative 5 if x is greater than or equal to 4. So the key to sketching this graph is going to be to look at each of these pieces separately. So for the first piece, I'll call this piece 1. We'll know that it's defined by y equals negative x squared plus 4, and that function is quadratic. And we also know that with the negative out front of that x squared, that it's going to be a downward facing parabola. So with a vertex of 0, 4. So we have those two key characteristics. Now, beyond that, we can also look at studying this function numerically. So we could make a quick table. Knowing this is a parabola, we should have a good idea of what it looks like, but we can make a table to get a bunch of those numerical values on our graph accurately. So we'll have x, and then we'll have negative x squared plus 4. And I need to know the values of this function at negative 3 and 3, and then in between. So I'll start with negative 3, and I'll put in negative 2, negative 1, 0, 1, 2, and 3. Okay, so if I input negative 3 into that expression, negative x squared plus 4, I'll have the negative of the quantity negative 3 squared, which will be negative 9, and then I'm adding 4. So that will end up at negative 5. Continuing in the same way for negative 2, I'm going to take negative 2, square it. I'll get 4, but I'm taking the opposite of that. So I get negative 4, add 4, and I'll be back at 0. And then at negative 1, I'll input that into that expression, and I'll get an output of 3. And at 0, I'll get an output of 4. And then at 1, I'll get an output of 3. At 2, I'll get an output of 0. And at 3, I'll get an output of negative 5. Okay, so we have function values for this piece. And so we'll look at putting them onto our graph. The key things that we need to keep in mind here is that we have negative 3 less than x, strictly less than 3. And so at negative 3, we're going to have an open circle. And the same thing's going to happen at 3. And that's because this is defined just between negative 3 and 3, but not including those values. So what that'll look like on this graph then is I'll go to the point negative 3, negative 5, and I'll put in an open circle. And I'll do the same at 3, negative 5. So for the rest of these points, I'll just complete then this parabola between negative 3 and 3. So I have the point negative 2, 0. I have negative 1, 3, I have 0, 4, I have 1, 3, and I have 2, 0. And so this first piece, then I'll connect them in a reasonably smooth curved piece there. Make that a downward facing parabola. Okay, but just between negative 3 and 3. Okay, so that first piece is good to go. Now, as we continue, this is going to be the graph of a single function. The only difference with the piecewise defined function is that different parts of its domain, or the function is defined by different main functions on different parts of its domain. So if we look at piece 2, we'll see that that's defined by y equals 2x minus 5. And that piece is going to be linear. So a linear function, generally if we were graphing y equals 2x minus 5, we'd identify that the y-intercept is 0, negative 5, and that the function has a slope of 2. And that would work here as well. But when we're graphing y equals 2x minus 5, but only for values of x for which 3 is less than or equal to x is less than 4, we really only need it to be graphed between 3 and 4. So the quickest way to draw the piece of this linear function is going to be to find that output value at 3 and the output value at 4. And then I know that I'll connect the function on those endpoints, from those endpoints, and that it should have a slope of 2 along there. So if I look, here I'll make a quick little table with x and 2x minus 5. And so at 3 and at 4, I want to know what those function values are. So if I plug in 3, I'll take 2 times 3 minus 5, that'll give me 1. And I'll plug in 4, 2 times 4 minus 5 will give me 3. And so here I can see that because I have this 3 less than or equal to x less than 4, at 3 I want a closed circle. I want the function to be defined at 3. But at 4 I'm going to want an open circle. I only want it defined up to 4, but not at 4 for that piece. So putting these on my graph then, I'll go to 3, 1, and again that's a closed circle, and then to 4, 3 with an open circle. And then I can connect those with a straight line with a slope of 2. So that's my second piece. Alright, I have the first piece and the second piece. Now I'll graph the third piece. So this is piece 3. And all I see is this negative 5. And so it's key to remember that if I were graphing h of x equals negative 5 for all values of x, that'd just be a constant function, which would look like a horizontal line. So what I'm really graphing here is y equals negative 5. And again, only for values of x that are greater than or equal to 4. So constant function, it's going to be a horizontal line, but I'm going to start at 4. So I'll go to 4, and then I'll go to 4, negative 5. So I've got that filled in circle at 4, negative 5. And then I will do all values of x greater than or equal to 4. So I'll make my horizontal line going to the right, and then I'll add an arrow. Again, that arrow is coming from the fact that x is greater than or equal to 4. So at this point, the graph of this piecewise function, so we've graphed y equals h of x, is complete.